It's time to begin planning a manned mission to Mars. In this segment of our multidisciplinary mission to Mars, you will be focusing on human survival. You will work with a crew of 4 to 5 specialists to address and solve the challenges that will need to be faced in order to ensure human survival on Mars for the duration of the mission. You will need to present models of your plans that clearly show how you intend to address the critical issues that will be faced when putting humans on Mars. Some questions to consider are: can humans survive on Mars, and how? What problems do we need to face and solve first? How can we accomplish short-term human survival? And how about long-term human survival? What would be necessary? In today's lesson, we're going to be going over a few key areas that are going to help you with your project. So that is Mars's position, gravity, atmosphere, terrain, radiation, temperature, and a lot of other helpful info as well. So pay close attention. Mars is the 4th planet from the Sun and the 2nd smallest planet in our solar system after Mercury. Mars is the outermost of the inner or terrestrial planets in our solar system. There it is. It is over 141 million miles from the Sun on average. That's nearly 50 million miles further than Earth's average distance from the Sun. A year on Mars is about 687 Earth days, so it's about twice as long as a year here on Earth. Mars has about 1/10 the mass of Earth, which contributes to its low gravity. Mars has about 1/3 of Earth's gravity. So when you're on Mars, like this fun little astronaut hopping around, you'd experience about 62.5% less gravity on Mars than you're used to here on Earth. We've discussed before how your weight is actually directly related to the gravity of the location you're at. So if you weighed 100 pounds here on Earth, you'd weigh about 38 pounds on Mars. Mars's thin atmosphere is composed mostly of carbon dioxide, whereas the atmosphere here on Earth is composed mainly of nitrogen and, of course, oxygen. Mars's atmospheric pressure is also worth noting. On Earth, the atmospheric pressure at sea level is just over 1,000 millibars, while on Mars it is only 7.5 millibars. Just to give you an idea, the atmospheric pressure at the summit of Mount Everest is still 300 millibars. So Mars's atmospheric pressure is extremely low. Due to that low atmospheric pressure, which is less than 1% of Earth's, liquid water cannot actually exist on the surface of Mars. Like Earth, Mars is differentiated into dense metallic core overlaid by less dense materials. But note in this image that on Mars, we don't see the liquid outer core. That's going to be really important when we start talking about magnetosphere. Besides silicon and oxygen, the most abundant elements on the Martian crust are iron, magnesium, aluminum, calcium, and potassium. The surface is thought to be mostly basalt, covered by a fine layer of iron oxide dust that has the consistency of talcum powder. So please consider this fine dust when you think about your designs. So Mars is often referred to as the red planet because of the reddish iron oxide prevalent on the surface that gives it a distinctive reddish appearance. Iron oxide, of course, is also known as rust. Surface features on Mars are reminiscent both of the impact craters of the Moon and of the valleys, deserts, and polar ice caps here on Earth. Mars's site, Olympus Mons, the largest volcano and the 2nd highest known mountain in the solar system, contributes to Mars's terrain. Mars has some of the highest peaks and lowest valleys in our entire solar system. Early in its history, Mars had a thicker atmosphere, allowing for liquid water. There is evidence that there was once liquid water on Mars in the form of rivers and likely lakes and oceans as well. In 2016, NASA reported finding a large amount of underground ice in the Utopia Planitia region of Mars. The volume of water ice in the south polar ice cap, if melted, would be sufficient to cover the entire planetary surface to a depth of 11 meters, or 36 feet. Though there is evidence that Mars once had an active core of molten metal, as we were talking about earlier, that would cause a magnetic field, its core no longer convects, and so its magnetic field is extinct and has been for a very long time. This will come into play when we start looking at radiation in a little bit, and for those of you who are thinking about looking into terraforming or otherwise shifting the climate of Mars, you're going to want to consider this. Mars is an extremely cold planet with average temperatures around -80 degrees Fahrenheit. Mars's thin atmosphere and its greater distance from the sun means that it is much colder than Earth. The average temperature is about -80 degrees, although it can vary from -195 degrees near the poles during the winter to as much as a comfortable 70 degrees Fahrenheit at midday near the equator in the summer. Because Mars has an axial tilt similar to Earth's, it does experience seasons. Giant dust storms routinely kick up the oxidized iron dust that covers Mars's surface. Dust is also permanently a part of the atmosphere, with higher amounts of it in the northern fall and winter and lower amounts in the northern spring and summer. The dust storms of Mars are the largest in the solar system, capable of blanketing the entire planet and lasting for months. These usually take place in the spring and the summer. Mars has no evidence of a structured global magnetic field or magnetosphere as Earth does. Mars's atmosphere was slowly stripped away by solar wind. Between the loss of its magnetic field and its thin atmosphere, the surface of Mars is exposed to much higher levels of radiation than Earth. That's solar and cosmic radiation. In addition to regular exposure to cosmic rays and solar wind, it receives occasional extreme blasts that occur with strong solar flares. The Mars Odyssey probe detected ongoing radiation levels of around 22 millirads per day, which are 2.5 times higher than what astronauts experience on the International Space Station. This works out to 8,000 millirads or 8 rads per year. The spacecraft also detected 2 solar proton events where radiation levels peaked about 2,000 millirads in a day, and a few other events that got up to about 100 millirads. For comparison, human beings in developed nations are exposed to, on average, about 0.62 rads per year. So compare that to the 8 rads per year that we're talking about. And while studies have shown that the human body can withstand a dose of up to 200 rads without permanent damage, prolonged exposure to the kinds of levels detected on Mars could lead to all kinds of health problems, like acute radiation sickness, increased risk of cancer, genetic damage, and even death. Be sure to study your Mars facts. Please take your Mars quiz, which can be found in Google Classroom by the end of the week. Additional resources that are really going to give you a lot of useful information for your project can also be found on Google Classroom. And trust me, a bunch of them are really fun. All right, now on to the project. You are now tasked with identifying and solving problems facing human survival on Mars. You will be working in crews of 4 to 6. Each crew member will be designated a role as a mission specialist. Think about your roles carefully. Within your crew, each specialist will be identifying and focusing on an essential problem that must. So here are the crew member roles. First, there's engineering shelter. This will most likely be one crew member, but if you have more than 4 crew members, you may have 2 people working on shelter. You'd be working on 2 different projects within the shelter category. So these crew members are responsible for designing aspects of the shelter that will ensure safety and survival so that humans can reliably live inside for short or long-term stays on Mars. Consider the following: radiation, air supply, power supply, waste management, water supply, gravity, pressurization, temperature, and keeping out potentially toxic or hazardous dust. We've also got engineering transportation. They're responsible for designing aspects of the transportation that will allow humans to safely and reliably travel on the Mars surface. Consider radiation, power fuel supply, terrain, gravity, withstanding dust or elements, temperature, spacesuits or self-contained vehicle. Do you need a spacesuit when you ride in your vehicle, or can you safely ride without one? All right, we've also got the biologist, nutrition and plant biology, responsible for designing and planning for a reliable food supply to feed all astronauts for short and or long-term stay on Mars. Consider resources that need to be brought to Mars, soil or plant food, location, will it be indoor, outdoor, above, underground, etc. Will you be using Martian soil? Will you be bringing soil? Energy sources, water supply, ease of growth, short or long-term supply, and quantity of supplies needed. We've got a chemist and medic, responsible for maintaining health of humans, responding to emergencies, and responding to potential hazards. Consider resources that need to be brought to Mars, radiation, pressure, ocular health, respiratory health, first aid, and we've got some optional roles. So we discussed the option of having a second shelter engineer. Can also have a crew lead responsible for overseeing crew efforts, coordinating Mars-based facility plans, meeting crew and specialist deadlines, assisting crew members with their projects, and maintaining the crew work log. Consider all of the above issues and roles because you'll be helping all of the crew members. Coordination, organization, and success of all your crew members' designs. There's also the optional role of field geologist. They are responsible for choosing an ideal location for the Mars base, addressing building concerns based on location and terrain. For extra credit, which we'll go over later, this specialist may also be responsible for research and long-term settlement solutions related to the planet's surface and tectonics. Consider Mars topography, Mars crust makeup, toxicity, tectonics, requirements for terraforming, and geoengineering. Together you will create a diagram of your Mars-based facility, pointing out general and any important information. Please indicate where on Mars your facility is located. We will talk about this in class. Each crew member will be designing a model that shows how they plan to approach the problem that they have identified. Each mission specialist is only required to select one problem within their scope to focus on, so don't worry and don't get overwhelmed by all those considerations. You'll only be focusing on one, unless you want to go above and beyond and maybe get a better grade. Models can be hand-drawn, computer-generated, three-dimensional, prototypes, or in the form of an experiment. At least one of your group's models must be three-dimensional or an experiment. At the end of the unit, you will be presenting your facilities and models to the class. Graded components for this project are going to be crew member web quests, which you'll see in your classroom. They're short. Identification of problems and possible crew solutions in the crew log. Pre-models, crew member models, facility diagram, crew logs, reflection, final presentation, and optional extra credit. It's time to do some research. Tomorrow in class, you will assign your crew member roles and get to work on your Mars facilities. Thank you for watching. Please follow the links provided to additional videos and watch them by class time on Tuesday. I recommend taking notes and writing down any follow-up or clarifying questions you may have. Be prepared to have discussions with your group about what challenges you may be facing in terms of human survival, and you will brainstorm any ideas you may have to begin your problem solving. This week, you should each have a vision of the specific issues you want to tackle and should also be completing your crew member web quest found in Google Classroom. All right, now get to work, Mars Explorers. I'll see you in class.